This is section 8.3. This is over graphing irrational expressions. So I know I've jumped around a little bit, and there's going to be kind of two parts to this. There's going to be two separate videos. One of them is going to be using your graphing calculator to kind of see what these graphs look like a little bit. So today the objective, students will be able to find holes and vertical asymptotes for rational functions and graph them using graphing calculators. So the first part, we have this vocab is a continuous graph and a discontinuous graph. A continuous graph is a graph that has no jumps, breaks, or holes. In other words, you can graph it without picking up your pencil at all. A discontinuous graph is graphs that are not continuous. So make sure you know those two, continuous and discontinuous. So we have a couple examples here, and in your notes I have those lines under there so you can label these. So if you were to graph this function, this is what it would look like. And if you were to draw this, over here it comes in and it goes here and kind of bounces back. But I could draw that without picking up my pencil at all, so that is continuous. Kind of spelled pretty sloppy, but that's okay, you guys get it. Then the next one, same thing, we have this graph over here, and if you try to draw that, what happens is there's actually a hole right here, because you cannot have -2 can't be your answer for this. And if you look, it actually kind of makes sense, because that's going to be where you have an undefined answer. If you plug in -2, there's a little bit more to that than just that it's undefined there, but that is why you can't have -2 be your answer. That's why there's a hole there. So this is discontinuous. And the last one, same thing for this one. You draw this down here, and then it all of a sudden comes up here and draws it on the other side. If you graph this in your calculator, that's what it's going to look like. So you have to pick up your pencil, so this too is discontinuous. And it deserves to be said, since I just said it about this one, again, that line right there is going to be at +2, where you can't get that. It's undefined at +2. So where you get something that's undefined, it's either going to be hole or vertical asymptote is what they call it. And we'll talk about that in a second. Right now is that second. So vertical asymptotes and solutions / roots. So a vertical asymptote is a vertical line that your graph jumps up or down where your variable is undefined. So for that last one we just talked about, this is an example of one with a vertical asymptote. This comes over here, and then all of a sudden it jumps up here, and it does that right here where the line is at 2, and that's because it's undefined right there. So that is a vertical asymptote. That's that jump in the middle. And it's always where it's undefined. You are going to start labeling it with a little dotted line. Then the other thing, an x-intercept is the numbers that makes the numerator equal to 0. So that is, the x-intercept is the same thing as your solutions, is the same thing as your roots. You've done this since you've done linear problems, and especially quadratics. Wherever you get your x-intercept, that's your solutions or your roots to a quadratic. Well, it's no different with these types of problems. So this is an example of a vertical asymptote. Again, your vertical asymptote would be about right here. And this is another one. Now, this is an interesting one, and a lot of the older calculators do this, the TI-83s, and some of the TI-84s. I think maybe mine still does. But when you do it, it goes up here, and your calculator, for some reason, can't just then start down here. So it actually looks like it goes up, and then comes down quick here, and then goes over. This middle part right here isn't actually a part of the line. So make sure you realize that if they just do that real sharp jump right there, your graph actually doesn't do that. So a lot of times your calculator will do something like this, and it goes, and then all of a sudden it goes and does the other end. That is not part of your graph. I don't know why it does that. The good news is the calculator's on your computer, I don't think does that. Or don't think, I don't know. I don't know if that's correct grammar, but that's okay. So let's talk about our x-intercepts. So remember back when we did x-intercepts, when we had stuff like this. When we did that, we did the cover-up method. So to find your x-intercept, we covered up the y. Well, why did we cover up the y? What does that mean? Well, it's actually because we plugged in 0 for y. So 6 times 0 is just 0. So it would be 4x plus 0, which is just 4x. So that's really why we covered it up, because really we were saying y is equal to 0. Well, it's no different. For what we're going to be doing now, it's the same exact thing. We want y to be equal to 0. So we're going to have a problem that looks like this. Y is equal to this. What could we plug in for x to make that 0? Well, you're going to look at your numerator, because if your numerator is 0, it doesn't matter what the denominator is, it's going to be equal to 0. So if you plug in -4, you're going to get 0 over -2. 0 over -2 is 0. That is where your x-intercept would be, at -4, not 0. But that's because that y is equal to 0 here. So in other words, it's always where your numerator is equal to 0. That's what I put right here. To get y is equal to 0, we have to make the numerator equal to 0. So for this one, our solutions or our roots or our x-intercepts is at x is equal to -4. And I really want you to put that x is equal to for all these. The next one then is vertical asymptotes. A vertical asymptote, and actually I should, before I start this, I should just make sure I specify. Don't think that if you get a 0 down here, if you plug in -2, that doesn't give you 0. That gives you undefined. That's different. So -2 is not our x-intercept. It's not our solution. The reason I jumped back and said that is because for our vertical asymptote, that's what we're looking for, is undefined. A vertical asymptote occurs where the function is undefined. In other words, a function is undefined when the denominator equals 0. So it's the same thing as our excluded values. So for this one, all we have to do is check what makes our denominator 0. So what would make this part 0? What would make it undefined? Well, this one's easy. That's -2. Because you get +2 over 0. Well, we can't have it over 0, so that is your vertical asymptote. Again, it's got to be x is equal to, because it's a horizontal line, or I drew it up correctly. It's a vertical line. So for our first question, we've already done this, and I put this little box in your notes for you. Your x-intercept is where your numerator is 0. Your vertical asymptote is where your denominator is 0. So we really already did this one. Our numerator is 0, x is equal to -4, so that's our x-intercept. And over here, our asymptote is x is equal to -2, because that's that vertical line. And again, I'm just going to keep both of them as x is equal to. I'm not sure how the other teachers do it. I know the vertical asymptote is always x is equal to, because it's a line. But technically, if I ask for your x-intercepts and you say x is equal to -4, I'm okay with that. I guess technically it would be an ordered pair, -4, 0. But again, I'm not going to fret too much about that, as long as you know what that is. So then we'll have problems like this, but the good news is they're already factored for us. So what would make our numerator 0? Well, what would make x minus 2 times x plus 4 equal to 0? Well, that would be +2 and -4. So my x-intercepts, x are equal to 2 and -4. What about our asymptotes? Well, we have x plus 1 and 5x minus 3. What makes that equal to 0? Well, we get -1 for one of them. And this one, if you can't figure out, again, you're going to have to solve this. But don't try to do these in your head if you can't. Add 3 to both sides. 5x is equal to 3. Divide by 5. X is equal to 3 over 5. So this one, I have 2 vertical asymptotes, which is fine. One of them is at -1, and the other one is at 3 over 5. We'll see a couple of those once we start the graphing calculator stuff. So go ahead and do this one on your own. Shouldn't take too long. Pause it, do it on your own, and then see what I get. So for this one, same thing. What makes your numerator equal to 0? This is your x-intercept. You could label that if you want. I haven't been, but if you want to be nice and organized, wouldn't be a bad idea. So subtract 4, 2x is equal to -4, divided by 2, x is equal to -2. Again, if you can't do it in your head, write it out like I did. Because I've seen people all the time where they try to do a shortcut and do it in their head and they end up missing it. So I would just always show my work. And then the other one, your y, or not your y-intercept, your vertical asymptote. What makes the denominator equal to 0? Well, this one's easy. That's +5 would make that 0. Then this one, again, if you can't do it, go ahead, write it out. What makes 3x plus 4 equal to 0? Subtract 4 from both sides. X is equal to negative 4 over 3. So remember, there's two of them for this one. We have these two. So I have x is equal to negative 4 over 3 and positive 5. Now, as you can imagine, it's going to get a little bit harder sometimes because you probably guessed this, but we have to factor now for some of these. But again, I know that some of you guys are sick of factoring, you're over it, but by now you should be really good at it where I get you don't want to do this problem by any means, but it's not a hard problem. You just have to factor. So let's factor out the numerator first. Factors of negative 6 that add up to be 1 are 2 and 3. 2 has to be negative. Luckily, we can take the shortcut. X minus 2 times x plus 3. And what makes the denominator 0? Factors of 8 that add up to be 6 are 2 and 4. They're both plus for this one. So x plus 2 times x plus 4. Now, you really don't have to think about it yet, but you can check. Make sure nothing cancels. If it does cancel, it's not necessarily a vertical asymptote, it's a hole. But we'll talk about that later. We'll talk about that once we get to the holes. Just wanted to plant that seed. So now, let's do our x-intercept first, since that's what we've been doing. What makes x minus 3, x minus 2 rather, and x plus 3, what makes that equal to 0? Well, that's good. Positive 2 and negative 3. Hopefully you guys are getting pretty decent at those. X equals to 2 and negative 3. And what makes x plus 4 and x plus 2 and x plus 4 equal to 0? I'm going too fast for my mind to keep up. If you need to solve it, you can. X is equal to negative 2, and this one, again, hopefully you don't need to solve those by this time. But our vertical asymptotes are at negative 2 and negative 4. So that would be, in our graph, they'd be vertical lines, and our graph would not actually touch those lines. They'd get close, but not ever cross them. Just like those pictures we did earlier. So do this one on your own. This one's not too bad because the numerator is already factored. Hit pause, do this one quick, and then watch me do this one once you're finished. So this one we have negative 15, and again, technically it's 1 times negative 15. Don't forget that. We just don't have a number in front, so we can go that negative 15 is fine. So that's 2 and 3. No, it's 3 and 5. Sorry. I saw that 2 and it stuck in my head. 3 and 5, and the 3 has to be negative, the 5 has to be positive. That's good. So x minus 3 times x plus 5. So what makes my numerator 0 is my x-intercept? Well, that's going to be positive 4. X equals positive 4. And for our denominator, we get positive 3 and negative 5. Again, what makes those two equal to 0? That's how I want you to think about it. I don't want you to think about it's the opposite of this and the opposite of this. I would rather you think what makes those 0. I think that's easier. Or easier in the long run, I guess I should say. All right, now we're going to skip ahead, or now we're going to get to the part where we're talking about finding holes. So holes are points on your function where x is an excluded value, but there isn't an asymptote there. So that's not the best of ways of describing it. So holes are points on your function where where x is an excluded value, but there's not an asymptote there. So far, all of the ones that we have that are excluded values that make the denominator 0, those have so far all been vertical asymptotes. Then it says, in other words, a hole occurs when a binomial cancels in the numerator and the denominator. So let's rewind a little bit. Let's go all the way back to those pictures we had. All the way back here, sorry. This one. We had a hole in this graph. And the reason we had a hole here, if I would have just given you this problem, you'd have said there's a vertical asymptote at negative 2. Because that's what makes the denominator 0. And this one, you would have been absolutely right. There's a hole at positive 2 because that makes the denominator 0, so it's undefined. So right here at 2, there's that asymptote. But the reason this one's not an asymptote is because if you look, there's an x plus 2 on top and an x plus 2 on the bottom. So really, this line ends up being, or this function ends up being y is equal to x plus 3. So 3 is our y-intercept. Our slope is 1. But that's what it cancels out to be, so that's what you would graph. But you still, even since you cancel this, remember before when I said even though you cancel it, it's still an excluded value? Same thing, just because I canceled it, you still can't have x be 2, or negative 2, sorry. So that's why there's that hole there. That's just that little open circle. So you'll always have a hole when you have something to cancel in the top and the bottom. So if you go through all the ones we just did, sorry, none of these canceled, the top and the bottom. X plus 4, x plus 2 doesn't cancel. None of that stuff cancels. That's why all those were asymptotes and not holes. The next one is the domain. The domain is a list of all the x values that our graph can have, and we'll write that as a set value. So the domain, we always talk about that, or we've talked about that before, where the x is equal to whatever all the x values is of our graph. X values are of our graph. For this one, really, we're going to write it in this notation, but actually all we're doing is we're just specifying where our x cannot be equal to. So every single one of these, don't make it hard. We're going to do a brace, x bar, so this means for all x's, and then x cannot equal, then it's whatever your excluded values are, it's wherever your holes or your asymptotes are. So I could have said my domain for all these. The domain for this one is x bar, and then x cannot equal positive 3 and negative 5. That's my domain for that one. Because all the x's work. You can plug in any x you want for that, except for 3 and negative 5. So again, if you have this, it tells you what it means for all x's, but x cannot equal negative 5. And again, we just plug in wherever our holes or asymptotes are. So now I'm trying to find my vertical asymptote, my holes, and my domain. One thing you do right away is your domain, we know is x bar, and then x cannot equal, sorry, that's sloppy. Should have given myself some more room. X cannot equal, and then we're going to put our holes or our asymptotes there. So let's get started with this one. I can factor out the denominator. Factors of negative 8 that add up to be 2. Well, let's see, we have 2 and 4. 2 is negative. So this is actually x minus 2 and x plus 4. We have x plus 4 on top. Then we have an x plus 4 on top and bottom, so I mentioned this very, very briefly at the beginning, but those will cancel. But when those cancel, there should be a little light bulb that goes off. That means we have a hole in our graph. Well, where's the hole going to be? Well, it's that place we just canceled. So we have a hole. What would make that 0? Negative 4. So we have a hole at x is equal to negative 4. So once we cancel those, we end up getting 1 over x minus 2. Since we have that x minus 2, now this didn't cancel, so we have x cannot equal positive 2, or I guess I should say that's where our vertical asymptote is. It makes our denominator 0. X is equal to 2. Now the problem with holes and graphing, and we'll talk about this once we get to the graphing calculator, your graphing calculator doesn't really have, the old ones didn't. I guess I'll have to check this one, but it doesn't really show your holes very well. It shows your asymptotes okay, but the holes are kind of hard to show in a graphing calculator, so make sure you can find those. But again, the only difference is these are both excluded values. Somebody asked that earlier last year, I believe, where they said, well, so what's the difference? So the vertical asymptote is an excluded value, but isn't the whole one too? Yeah, these are both excluded values. We know that x cannot be equal to positive 2 and negative 4, and that is our domain. X cannot be equal to 2 and negative 4. Sorry, I have to write really small. I should probably move that over. But that's our domain. X cannot be equal to those. But the difference is one of them cancels, so it's a hole. The other one is a vertical asymptote. It doesn't cancel. This one's really fancy. We got a lot of factoring with this one. So we have factors of 6 that add up to be 5. are 2 and 3. So we have x plus 2, x plus 3, over, I have factors of 3 that add up to be 4 are 1 and 3. 1 times 3 is 3. 1 plus 3 is 4. So I have x plus 1, x plus 3. So now we see if we can cancel anything. Well, we have an x plus 3 on top and bottom, so those cancel. So again, that bell should go off in your head. One of our holes is at -3, because that's what would make this 0. So what do we have left? We have an x plus 2 over x plus 1. So our vertical asymptote is what makes that denominator 0. X is equal to -1. Technically, our y-intercept for this one is going to be -2, but it doesn't ask, or sorry, our x-intercept. It doesn't ask for that, so we don't have to worry about it. Our last one didn't have an x-intercept. And our domain for this one, again, we have x bar, x cannot equal, and then we have both of those, -1 and -3. Both of those don't work. And that, again, the domain is just our excluded values. You're just listing both your holes and your vertical asymptote. So do these last two on your own. We only have one to factor for this one. So again, pause it, do this one. You guys should be used to this now. We have factors of -12 that add up to be 1 are 3 and 4. But the 3 is going to be a negative. So we have x minus 3, x plus 4. On top we have an x minus 3. So we have an x minus 3 on top and bottom, so they cancel. If something cancels, you know it's got to be a hole. X is equal to +3. That's where there's a hole. Then we end up getting 1 over x plus 4. So that then means we have an asymptote at x is equal to -4. And for our domain, we have x bar, x cannot equal, both of those, 3 and -4. Now, people have asked me before, it doesn't make sense. How can we put the x is equal to here, and over here we say x is not equal to? We have x is equal to 3, but x is not equal to 3. Well, the reason is because the reason x, and this is going to be confusing, I guess the short version is, just put it that way. Don't think about it, just do it. But the reason is because x cannot equal 3. The reason x cannot equal 3 is because there's a hole there. The hole is equal to 3, so x cannot be 3. The asymptote is x is equal to -4, so x cannot equal -4. So that's the real reason. But again, if that's confusing, just remember your domain, just put it as does not equal to, x does not equal to 3 or -4. And for your asymptotes and holes, you're just saying where they are at, and so put x is equal to for those. And the last one, again, we are doing factoring. So 1 times -24, add up to be -2. That's got to be 6 and 4, and the 6 is negative. X minus 6, x plus 4. And again, you guys, hopefully by this point, you guys are flying through this factoring. So that's +12. Factors of 12 that add up to be 8 are 6 and 2. They're both negative. Be careful with that. X minus 2, x minus 6. So those 6's cancel, which immediately means we have a hole at 6. When we solve this one, then we have x plus 4 over x minus 2. So our vertical asymptote, x is equal to 2, because that would make it 0. That would make it undefined at 0. And your domain, x bar x cannot equal 2 and 6. Oops, that should be a brace. All right, so that's the first part of this lesson, is just making sure you know how to find the vertical asymptotes, the holes, the domain. Technically, I could have you guys graph this by hand. You would just have to plug in some numbers, find x-intercepts, y-intercepts. But instead of doing that, we're going to have you guys use your graphing calculators. That's going to be on a separate video. So make sure you watch that one as well. If you have any questions, make sure you email me.